All right. Hello, everyone, and welcome to another deep dive. This time, we're tackling something that's been generating a lot of buzz lately: the future of quantum computing.
That's right. We'll be peering into the quantum crystal ball, so to speak, trying to get a glimpse of what the next 5, 10 years, and maybe even further down the line might hold for this game-changing technology.
Exactly. And for those of you who might be new to this quantum world or maybe just need a little refresher, where do we even stand right now with quantum computers? They're not just science fiction anymore, are they?
Not at all. We've moved past the purely theoretical stage. Quantum computers are real, they're here, and they're doing calculations. But, and this is a big but, we're still very much in the early stages.
It's like we've just launched the quantum Sputnik.
Right.
Right. A huge first step, but still a long way from a fully operational space station.
Yeah.
So where are we exactly on this quantum journey?
Think of it like this. We're in what experts call the noisy intermediate scale quantum era. It's a bit of a mouthful, I know, but it basically means that the quantum computers we have today are still quite limited.
Limited in what way?
In a couple of key ways. First, the number of qubits, those quantum bits that hold information, is still relatively small. And second, these qubits are still quite prone to errors. That noise in the name refers to these errors, which makes the computations unreliable sometimes.
So kind of like the early days of computers with those clunky machines that took up entire rooms and spit out punch cards.
Yeah, there are definitely parallels. We've come a long way since those days. And similarly, we're making significant strides in quantum computing. But we're not quite at the point where quantum computers are going to replace your laptop or smartphone anytime soon.
Speaking of strides, there was all that excitement a while back about Google achieving quantum supremacy with their Sycamore processor. What was that all about?
Ah, yes, the quantum supremacy demonstration. That was a significant milestone, no doubt. What Google achieved was pretty remarkable. They designed a specific task, a rather abstract mathematical problem, and their Sycamore processor solved it significantly faster than any classical computer could. It was a clear demonstration of the potential power of quantum computing.
I remember some pushback at the time, though, right? Like people questioning whether it was truly supremacy or just a clever trick.
You're right, there was some healthy debate. Some argued that the task itself was a bit contrived, designed specifically to favor a quantum computer. And they pointed out that with further refinements, classical algorithms and supercomputers might be able to catch up, maybe not surpass, but at least come close to the quantum performance.
So it was a bit of a hold your horses moment for all the quantum hype.
You could say that. It emphasized that while we've shown quantum computers can outperform classical ones for certain problems, the real challenge is finding problems where that advantage is truly meaningful, practically useful. And that brings us to the concept of quantum advantage.
Quantum advantage. That's about solving real-world problems, right? Not just winning in a carefully constructed quantum obstacle course.
Precisely. Quantum advantage is all about demonstrating that a quantum computer can solve a real, practical problem significantly faster, better, or more efficiently than any classical computer, even with all the clever algorithms we have today.
So it's not just about speed for speed's sake, but about solving problems that actually matter. And to do that, we need better quantum computers, right? With more qubits, less noise, all that good stuff.
Absolutely. And the good news is we're seeing tremendous progress on that front. The race to build bigger and better quantum computers is on, and it's heating up.
Oh, tell me more. Who are the major players and what kind of advances are we seeing?
Well, you've got big names like IBM, Google, Rigetti, IonQ, just to name a few. They're all pushing the boundaries of what's possible.
And are they all using the same approach, or are there different ways to build a quantum computer?
Actually, there are different approaches. It's a bit like the early days of flight, where you had folks experimenting with all sorts of contraptions, trying to figure out what worked best. In quantum computing, some are using superconducting qubits, which need to be kept incredibly cold, close to absolute zero. Others are working with prepped ions, individual atoms held in place by electromagnetic fields.
So a real mix of cutting-edge technology. And how are they doing? What kind of qubit numbers are we talking about?
IBM, for example, recently unveiled their Eagle processor, boasting a whopping 127 qubits. And they've already set their sights even higher, aiming for a 1,000 qubit processor called Condor in the near future.
That's a huge jump. Are the other players in the same ballpark?
They're all making impressive strides. Rigetti, also using superconducting qubits, is pushing the limits in terms of connectivity and control. And IonQ, with their trapped ion approach, is achieving remarkable levels of qubit quality and coherence time.
Coherence time. That sounds important. What exactly does that mean?
It's crucial, actually. You see, qubits are incredibly delicate. They're prone to losing their quantum information, their quantumness, if you will, due to interactions with their surroundings. This process is called decoherence, and coherence time measures how long a qubit can hold on to its quantum state before decoherence sets in.
So the longer the coherence time, the more time we have to perform calculations before the quantum information fizzles out.
Precisely. It's like trying to build a sandcastle on the beach. The tide is constantly coming in, threatening to wash it away. The longer you can keep the tide at bay, the more elaborate your sandcastle can be.
And we need those elaborate sandcastles, those complex calculations to solve those big real-world problems we were talking about earlier, right?
Absolutely. That's why researchers are constantly working on improving coherence times, developing new materials, and refining techniques to isolate qubits from their environment as much as possible.
So it's a constant battle against decoherence. And even if we manage to keep the qubits coherent for longer, they're still prone to errors, right? Those pesky little quantum hiccups.
That's another major challenge. Even with improved coherence times, errors are inevitable, and these errors can quickly accumulate and mess up the entire computation.
So we need a way to catch and fund those errors, like a quantum spell checker.
Exactly. And that's where quantum error correction comes in. It's one of the most critical areas of research in quantum computing. The idea is to encode quantum information across multiple physical qubits, creating a sort of redundant shield against errors.
Like having backup dancers for your star performer.
A great analogy. If one dancer stumbles, the others can keep the routine going. Similarly, if one qubit goes astray, the encoded information can be recovered from the others.
So it's all about building resilience into the system. And how are we doing on that front?
There's been significant progress in developing these error correction techniques. One promising approach is called the surface code, which is particularly well suited for certain types of quantum hardware.
So we're making headway in taming those quantum errors. But we need more than just robust hardware, right? We also need the instructions, the algorithms, to tell these quantum computers what to do.
Absolutely. That's where the software side of things comes in. And just like we need specialized hardware for quantum computing, we also need specialized algorithms. We can't simply take classical algorithms and run them on a quantum computer.
So we need a whole new way of thinking about programming.
In a way, yes. Quantum algorithms need to be designed from the ground up to exploit the unique properties of quantum mechanics, those mind-bending concepts like superposition and entanglement.
Well, there we go again, with the quantum weirdness. Could you remind us what those are all about? I always feel like I'm grasping at smoke when I try to wrap my head around them.
Well, imagine a coin spinning in the air. Until it lands, it's both heads and tails at the same time, right? That's kind of like superposition. A qubit can be in multiple states simultaneously, not just a 0 or a 1 like a classical bit.
So it's like a quantum multitasker. And what about entanglement?
Think of two coins spinning in the air but somehow linked together. If one lands heads, the other instantly lands tails, no matter how far apart they are. That's entanglement. It's like a spooky connection between qubits.
It's enough to make your head spin. But these weird quantum properties are what give quantum computers their power, right?
Exactly. They allow quantum algorithms to explore vast computational spaces simultaneously, to perform calculations in ways that classical computers simply can't.
So what kinds of problems can these quantum algorithms solve? What are they good at?
There are a few key areas where quantum algorithms show great promise. One is optimization. Think about finding the best route for a delivery truck, the optimal schedule for a factory, or the perfect allocation of resources in a complex system. These are all optimization problems, and quantum algorithms are showing the potential to find solutions much faster than classical approaches.
So quantum computers as super efficient planners and organizers. That sounds pretty handy. What else?
Another area is simulation. Imagine being able to simulate the behavior of molecules at the atomic level. This could revolutionize drug discovery, materials science, and our understanding of complex chemical reactions.
So instead of years of lab work, we could run virtual experiments on a quantum computer and see how molecules interact in real time.
Precisely. And with much greater accuracy and detail than we can achieve with classical simulations. It's like having a super-powered microscope that lets us peer into the quantum world.
That's amazing. And there's something else, right? Something about quantum computers helping with artificial intelligence.
Yes, that's another very exciting area of exploration. There's a lot of potential for synergy between quantum computing and AI.
Synergy, so they can work together, like a dynamic duo.
Exactly. Quantum computers could potentially supercharge AI in a few ways. They could help train AI models much faster, allowing them to learn from larger data sets and identify more subtle patterns. They could also enhance the optimization capabilities of AI algorithms, leading to better decision-making and problem-solving.
So quantum computers could be like personal trainers for AI, helping them bulk up and reach their full potential.
You could say that. And it goes even deeper. Some researchers believe that quantum computers could enable entirely new types of AI, algorithms that operate on fundamentally different principles than what we have today.
Quantum-powered AI. It sounds both exciting and a little daunting. Like, what kind of intelligence could emerge from that combination?
That's one of the big questions, and it's one that we're only beginning to explore. But it certainly has the potential to be revolutionary.
So we've got these incredible potential applications. We're seeing significant progress in hardware and software. But what are the biggest challenges ahead? What's holding us back from this quantum future?
Well, as we've discussed, decoherence is a constant adversary. Keeping those qubits coherent for long enough to perform meaningful calculations is a major engineering challenge. And even with longer coherence times, error correction remains crucial.
It's a bit like trying to juggle chainsaws while riding a unicycle on a tightrope, right? A lot can go wrong.
It's certainly a delicate balancing act. And on top of those technical hurdles, we also need to think about the ethical and societal implications of this powerful technology.
Oh yes, the ethics of quantum computing. That's a whole other can of worms.
Indeed. As we develop more powerful quantum computers, we need to consider how they might be used, who might benefit from them, and what the potential downsides might be.
Like the potential for quantum computers to break encryption and compromise cybersecurity.
That's one concern, yes. If quantum computers become powerful enough to crack the codes that protect our online transactions, our communications, our entire digital infrastructure, we need to be prepared.
So we need to develop quantum-resistant cryptography, essentially build a new digital fortress.
Exactly. That's already an active area of research. And beyond cybersecurity, there are broader ethical considerations. For example, if access to quantum computing becomes concentrated in the hands of a few, it could exacerbate existing inequalities. And we need to think about the potential impact on the workforce. As quantum computers automate certain tasks, some jobs might become obsolete.
It's a lot to grapple with. But it's important to have these conversations now, right? As we're building this technology, we need to be thinking about how to use it responsibly and ethically.
Absolutely. It's crucial to engage with these questions proactively to ensure that the benefits of quantum computing are shared broadly and that we mitigate the potential risks.
So it's not just about the science and engineering, but also about the societal impact. And it sounds like there's a lot of international activity in this field. Is it a race, a collaboration, or a bit of both?
It's a bit of both, actually. There's definitely a sense of national competition with countries like the US, China, and those in the EU investing heavily in quantum research and development. But there's also a strong spirit of collaboration within the scientific community.
So it's like a friendly rivalry where everyone's pushing each other to be better, but also sharing knowledge and resources.
Yeah, that's a good way to put it. And it's this combination of competition and collaboration that's driving the field forward at such a rapid pace.
It's fascinating to watch it all unfold.
Yeah.
So for our listeners who are curious about this quantum future, what's the best way to stay informed, to learn more about this complex and rapidly evolving field?
Well, there are some great resources available online. IBM, for example, offers the Quantum Experience, which allows anyone to experiment with real quantum computers through the cloud. Microsoft has their Quantum Development Kit, which provides tools for building and running quantum algorithms. And there are numerous online courses and tutorials that cater to the different levels of expertise.
It sounds like there's something for everyone, from the curious beginner to the seasoned quantum expert. And it's exciting to think that we're all witnessing the birth of a new technological era, one that could fundamentally change the way we live, work, and interact with the world.
It's a truly transformative time to be alive. And while there are certainly challenges ahead, the potential benefits of quantum computing are so vast that it's well worth the effort.
Thanks for taking this deep dive with us. We hope you found it insightful and maybe even a little mind-bending. Until next time, keep exploring, keep questioning, and keep decoding the quantum world.